Good morning. Now we'll be discussing another problem on tray towers, absorption on tray towers. Again, I will read the question and discuss about the problem, what is the problem statement and what is to be done and how is to be done. That I will, even though I have explained it in the previous problem, once again I will discuss. Then you see that this is the same problem which you have done in packed column. Same question, the same operation if you are doing on a tray tower. What will be the height pressure drop? What will be the height pressure drop? And we are going. So first part will be more or less same, but you should do it because then only you will get experience. So that if you do more number of problems in the examination hall, you will be able to do it in a faster way. Now, experience make a man perfect, So, try to complete without copying it from the previous. You do it by yourself. The question is acetone air mixture containing 6% of acetone by volume at 298 Kelvin is to be scrubbed with water to remove acetone. Design a plate tower in such a way that 98% acetone must be removed for a feed rate of 3000 meter cube per hour of gas. The equilibrium data is y star is equal to 1.68x. Assume dilute system behavior. Design the tower diameter and height and check the design for all parameters. So again, I think I don't have to explain it once again. This is you say the tray column. Tray column consists a column in which trays are kept at definite intervals of time. There are n number of trays. The liquid will come from the top and the gas will be admitted from the bottom of the tower. And as they travel, they will be in intimate contact at the plate. And so transfer of solute from the gaseous phase to the liquid phase takes place at the plate. In between, there won't be any transfer. That is what we are assuming. Whereas in the packed column, the continuous exchange of solute from the gas to the liquid takes place continuously. Then again, once again, I will show you the notation. Here you see that the tray is numbered from top to bottom, 1, 2, 3, n minus 1, n, and the gas will go from top. The notation for the gas which is coming from the nth plate is Gn. Gn minus 1 is the gas molecular flow rate from the n minus 1th plate. Like that, G3, G2 and G1 is the gas coming out of the tower. Gn plus 1 will enter because I told you Gn plus 1 is a fictitious plate. Such a plate does not exist, but we assume that it will be from the storage. Where is the gas coming to the column? It is coming from a storage tank through pump or whatever way. So Gn plus 1 represents the storage tank. Similarly, the liquid comes from the top. Then the liquid which moves from the first tray is called L1, L2, L3, like that. And finally, it comes from the bottom as Ln. So the liquid entering is denoted by L0, and then X0 is the concentration of the solute in the liquid. Usually, the solution will be, the solvent will be pure, so X0 equals 0. But sometimes, if used water is available, which may contain a very small amount, X0 should be 0.0005 or something like that. That can also use reusing of the water which has been used. In industry, we cannot waste water. So, and there is no point in making it fully, making it 100% pure. So, you can use some X0 can have the value of 0.005, something like that. So, I think the problem as far as the tower is concerned, I have explained. And inside the tower, the liquid will flow. If you see, enter from the right side, and it will flow across the cross section of the plate or the tower, and through the downcomer it will come to next tray below that. So that is the 70%. The diameter of this plate will be 70 to 80% of the tower only. So, and the gases from the bottom will go through the holes, and the liquid will through the downcomer. It comes and flow across the diameter, and then they will have a intimate contact between. So the intimate contact between the liquid and the fluid, liquid and the gas, and there will be the froth will be formed. So this froth will have a volume area will be high, and so good mass transfer takes place. Here I have shown the arrangement in which the bubble caps are arranged on a tray. So I think now and you refer peri and go through it, then it will be thorough. Next we have to find and what are all the parameters given. This is liquid flow, gas flow rate is given. Then acetone inside the concentration of acetone in the incoming stream is given. And how much acetone is to be removed is given. Equilibrium data is given. But the amount of solvent is not given. How much water is to be used is not given. So you have to find out the minimum, to find the number of stages, minimum amount of liquid is to be found out, and then you have to take 50% above that. Now coming to how will you do the design procedure. You have to find the number of plates or stages from graphical procedure or using Kramser equation, because it is given dilute solution and M is a constant also. So actually what they want is they won't expect you to do it by constructing the graphs. Instead of that, you memorize Kramser equation. And there is a difference in the Kramser equation from the plate column, packed column, plate column, packed column. Study well, understand the terms, and by heart it, and reproduce in the answer. Because if you are using that equation, you will a lot of time can be saved. Otherwise, you have to plot and then find the number of triangles. So memorize this equation. Next, you have to find out the column diameter from empirical equations. Now, by the time you would have been very familiar with these empirical equations. Then downcomer segment area, tray layout. The tray layout means how many caps, bubble caps, or how many sieves are to be there, and how they are arranged. Pitch. What is pitch? Pitch is the center to center distance of two sleeves or two slots. Then tray thickness. After we assume tray spacing. Here what will you do is, instead of packed column, in a packed column we find the height equivalent to a theoretical plate. But here we assume for 50 mm or 500 mm, and then we check for the pressure drop. So many design checks. One is pressure drop. What is pressure drop? Now you may be familiar. That is how much is the pressure difference between the lower column and the plated first plate and second plate, or in between two plates. This is, you will get it as in millimeters of water, and millimeters of water we have to check with the atmospheric pressure. So there is a pressure. If it is very low pressure, then we can say that design is okay. Then weeping. Weeping is, what is weeping? The flow of liquid through the sieves. The liquid is supposed to flow through the downcomer. If it is not coming through, if the pressure velocity of the gas going up is not sufficient, then not high, then what happens? It will leak through that is weeping. Then liquid hold up. Liquid hold up also I have told you, by the time you would have been very familiar with it. That is also available in 7th edition. Weeping also available in the 7th edition. Liquid hold up is what is the total hold up. That means in the tray there is a wire, and that wire has got some height. You assume it is to be 40 mm or 45 mm, and length is 80% of the diameter. That is the length of the wire. So height of the wire is you assume that 40 mm or something like that. So you have to find out. Then this height, this space 40 mm will be occupied by both froth and liquid. Liquid is a small pocket of liquid, and above that the froth will be. So you have to find you have to find out that you will hold up, and it is to be checked. Then entrainment, downcomer flooding, downcomer loss. Entrainment, you know what is entrainment? The amount of liquid that is carried away by the gas. There is an equation for that. Then downcomer flooding, that has contains two parameters, downcomer loss and downcomer backup. You check all these things, and if all the parameters are met within the specified limit, then you can say the assumed height is, trace spacing is okay. How will you find the height? Total height is equal to, if there are 10 number of plates, there will be 9 spaces in between. If it is 15 means 14 spaces. So you have to subtract 1 from the total number. If it is 7, 6, the space will be 6 into 450 plus 1.5 meter you leave at the top and bottom. 2 into 1.5. This is the height. Now, I assume some efficiency also. In that case, the number of 50% means, if the 6 is the number of stages without assuming efficiency. If efficiency is 50%, then 6 will double. 12 there we require 12 plates. So you calculate accordingly. So the design is okay. Now again you go to the data. That volume is given as 300 meter cube per hour. That is Vn plus 1. The notation is, that is gas is coming from the bottom and it is coming from the n plus 1 the plate. So Vn plus 1 is 3000 meter cube per hour, and the velocity per second, it is 0.83 meter cube second. Then Yn plus 1 is equal to 0.06. T is equal to 298. P is equal to 1.0135 into 10 raised to 5. And M is the equilibrium line slope, 1.68. And 98% of acetone is to be removed. Now, the data volumetric flow rate is given in meter cube per hour or meter cube per second. So that you have to convert it into moles. In absorption, you deal with moles. So how will you find out the mole? You use PV is equal to nRT. We know R from the table. You take now. You may be knowing it in by heart. 8.3114 into 10 raised to 3 Pascal per meter cube, kilogram mole per Kelvin. Because you note here, this is kilogram. All you are dealing with kilogram mole. So in the R, if you refer Perry, it will be given as 8.314 Pascal meter cube per mole Kelvin. That mole means gram mole, but that is understood. If you are telling mole means it's gram mole, so you have to convert into kilogram mole, and then to make gram mole to kilogram mole at the bottom, this gram mole is at the denominator, so you have to multiply with 10 raised to 3, and n you find out. Then you have to find out capital Yn, small yn plus 1 is given. What is for small yn plus 1? Mole fraction. Capital Yn plus 1 is mole ratio. Mole ratio is to be found out using the equation Yn plus 1 divided 1 minus Yn plus 1. So this is not 64. This 98% is to be removed, isn't it? 98%. So 2% will be left in the outlet. So GS you can, that is 0.02 of Yn plus 1. That is 0.00128. That is capital Y1. Then you find out small y1. All these things, now you are very thorough with it. Then find out GS. GS, what is GS? GS is the molar flow rate of pure air. There is no, if you subtract acetone, what is the data? That is volume of the feed entering the column is given as 3000 meter cube per hour, which is Vn, notation is Vn plus 1. That gas which is entering into the column has got the subscript n plus 1. Since it is volume, we put it as Vn plus 1. What we require is Gn plus 1, that is molar flow rate. Here hour is to be converted into second, and Yn plus 1 is given, that is the mole fraction of acetone in the feed. Note 6, temperature is 298 Kelvin, pressure is 1 atmosphere, M is the equilibrium line slope 1.68, and 98% of acetone is removed. Now to find out the Gn plus 1, Gn plus 1 is PV, you have to use PV equals nRT, all the values are here. Find out n, and you be careful that this equation can be used only for gases. For liquid this cannot be used. So n you are getting is equal to 0.034, that which is Gn plus 1. Then to find out 98% is to be removed. So for that you have require mole ratio, that is capital Yn plus 1 is equal to small yn plus 1 divided by 1 minus Yn plus 1, 0.06 by 0.94, 0.64, and then Y1, that is the amount of gas in the outlet stream, is 2% of Yn plus 1, that is 98% of acetone is to be removed. So 0.02 into 0.064, which is 0.00128. Then this is capital Y1, small y1 will be slightly less than that, 0.00127. Now Gs is the amount of pure air. It is Gn plus 1, if you know Yn plus 1, that can be determined. It is coming around 0.03196. Then G1 is, that is, again you have to make use of the relationship Gs is equal to G1 into 1 minus Y1. So G1 is equal to Gs by 1 minus Y1 is 0.032. And acetone in the outlet stream, that is mole ratio Y1 is equal to 0.064 into 0.02, that is 0.00128. Then Y1, that is small y1, mole ratio is also mole fraction and mole ratio are more or less equal when the it is very dilute solution. G1 is also obtained. G1 also you calculate. Then pure water is pure. Assume pure water. So X0 is equal to 0. You don't know what is Xn. The quantity is also not known. Here, since the amount of liquid is not given, you have to assume a minimum and then take 1.5 times the minimum and find out the actual amount of water liquid. Slope of the equilibrium line is given as 1.68. Now you have to find the how much minimum required, minimum amount of fluid required. For that you plot X versus Y, that is mole fraction. You need not consider mole ratio coordinates because the system is dilute. Equilibrium line you construct. Then when you select the axis, be careful. The x-axis should vary from 0 to 0.1. Y-axis also 0 to 0.1. Draw the equilibrium line with slope 1.68. First, mark the point bottom of the tower. Bottom of the tower will be having the maximum amount of gas coming. So the coordinates are xn and yn plus 1. Yn plus 1 is known, but xn is not known. Then at the top of the tower, the coordinates are x0 and y1. x0 is known and y1 is also known because you have already found out. x0 is equal to 0. Then now what we have to do is xn is not known, yn plus 1 is known. Yn plus 1 is equal to 0.06. For after drawing the equilibrium curve, mark the point, draw the horizontal line, mark 0.06 in the y-axis. take 0.06 on the y-axis and draw a horizontal line from 0.06 to meet the equilibrium line. The xn will lie on this line. We don't know the actual xn where will lie. So then B will be x0, 0.6. Mark A, that is x0, y1. x0 is 0, y1 is equal to 0.00128. This will represent the top of the tower. You can see that top of the tower, the gas is lean, liquid is pure. So it will be near the origin. That is why 0 and 0.00128. Join AB. From the graph, we will get that x1 is equal to 0.035 and y1 is already known, 0.06. Find the slope. Slope is coming at 1.668. Now, the slope of that means the slope of the operating line corresponding to minimum LS by GS is 1.668. But actually, how much so from this we will be getting LS by GS is equal to 1.668. LS minimum is equal to 1.668 into 0.032, it is 0.0533 kilogram moles per second. So actually you have to take 1.5 times. So LS by GS into 1.5 you will get 2.5017. This is the actual amount of liquid required, and this is the slope of the actual operating line, 2.51. Then you have to find out, draw a line from AB, that B dash, then draw the line AB dash with slope 2.5017. Then B dash is the point, it is 0.034. That is, the x1 is equal to 0.034. And find out the actual slope will be, from the slope also you can find out the amount of xn. So this is now the amount of acetone in the exit water stream is 0.0234. Now then you construct graph between the operating line and equilibrium line. Now I got from the graph at 9. Actually in your previous example you would have done it. It's exactly one and the same. There is no change, but you do it once more so that you will be thorough with the procedure. And mind that this minimum solvent required will be used if and only the value of the solvent is not given. If the amount of solvent is given, then you need not do this exercise. You can, L is known, so LS is known, GS is known. So find out the slope. Operating line slope is LS by GS. Then you straight away construct the operating line and construct the triangle. So next we have to find the diameter of the column. How do you find the diameter? Diameter of the column, from the volumetric flow rate of the gas, because you have to take the volumetric flow rate which is higher. In the case of always, usually the gaseous flow rate will be volume-wise, gaseous flow rate will be more. You have get it 0.83 meter cube per second. Then what you have to do is, you have to find to get the diameter, we require area. To get area, you have to divide the volumetric flow rate divided by velocity. Velocity is determined using empirical relationship. For that, from figure page 1437, 8th edition query, equation 1489 says FLG is equal to L by G into rho G by rho L raised to 0.5. What is FLG? FLG is a flow parameter. You know all the values. L is known, G is known. L and G are the mass flow rate. So you have the molecular flow rate. You convert it in, multiply with molecular weight and convert it into mass flow rate. That is shown here. Then you find out the value of FLG and assume here, you assume a trace spacing of, again 450 mm, we can assume that will be safe. From the trace spacing of 450 mm, from figure 1431 of page 1438, a plot you can see, that is FLG is plotted against FLG is plotted against some parameter. You can the CSB. Here for FLG of 0.054 and 450 mm trace spacing, find the value of y-axis, that is CSB is equal to 0.088 meter per second, and from the coordinate, from the what is CSB? CSB is equal to velocity into sigma by, or velocity is equal to CSB into sigma by 20 raised to 0.2 Royal minus rho g by rho g raised to 0.5, and you can calculate VNF. It is, this is flooding velocity, it's 1.54 meter per second. You assume 80% as the actual velocity, you will get 1.23 meter per second. Find out the area, that is active net area. Net area will be divided by volumetric flow rate divided by velocity, you get 0.669. Then assume that is AD is the downcomer area. Assume that 10% of AT. So you can find out the AT, that is AN plus AD is equal to AT. So AD and AT, the relationship is 0.1. So you get AN as AT divided AN by 0.9. You get 0.7744. Find out the diameter using the, for a circular pi by 4 d square, you find out d 0.973. And the downcomer segment area I am leaving for the time being. From this, what you get is the chord length. To get the chord length only we are using it. Instead of chord length will be, this chord length will be the length of the wire. So you can assume some 70 to 80% of the diameter as the. So this exercise you need not if you are not very sure about it. Here the tray layout is shown. Now we have to find out how many number of trays are there. So they assume that 6%. The whole area is H is the whole area. Is assume that it is 6% of the total this area, active area. Then we have to find out from AA. If you find out AA is available, AA is AN minus AD. Then AH is equal to 0.064. Find out 0.03, that is area of holes will be 0.03. That is total. How many holes are there? We don't know. The total area is given 0.357 meters square. Then assume one hole diameter is 10 mm with a pitch, equilateral triangle pitch. I have already. What is pitch? Pitch is the distance between the two, the center of the slots or sieves. Area of one hole is pi by 4 d squared, which comes around 7.85 into 10 raised to minus 5. Find the number of holes from the total area. Total area is 0.0357. Total in the sense whole area. Total whole area is not 0.0357, and whole area of one hole is 7.85 into 10 raised to minus 5. So number of holes is 454. It should be a multiple of 6. So it comes around 456. Then you find out the pitch. That is also straightforward. A is equal to n into root 3 by 8 a squared 2, which is the equation for equilateral triangle area. Find out A is coming out to 38 mm. It should be between 25 to 30. So design is okay. Next is tray thickness. Tray thickness, again assume that TT by DH is equal to 0.5. It should be between 0.2 to 0.7, and find out the thickness. It comes around 5 mm. With this, the design is over. Now, next we have to check for the design adequacy. Next you have to find out the pressure drop. Pressure drop HT, total pressure drop is equal to HT plus HL dash. HD is the pressure drop across the dispersion unit, and it is there is a formula to find out HD. K1 plus K2 into rho G by rho L UH raised to 2 UH squared. K1 is for sieve plate, K1 is equal to 0. K2 is equal to, there is a formula to find out K2. Then HL dash is the pressure drop through the aerated mass over and around the dispenser. Disperser means this slots, no, sieves, that is called the dispersion. There only dispersion takes place, and HL dash is around the downcomer. So what you have to find out is, we have to find out beta. Next is beta. We have to find out. There is a formula, and HDS is obtained by HW plus HOW plus 0.5 HHG. You see the figure and try to learn by yourself. If you have any doubt, you ask me. HW is the height of the wear. What is the lip of the wear? Actually, the where there is an extension, we can assume it is a 40 mm, and HOW is the height of the crust over the wear. I have, in the last class, I have told the lip of the wear is not flat. It is slightly inclined. So when the water flows from the overflows through the wear, there is a height that is called HOW. There is formula to find out HOW. Then next is HD is equal to K1 plus K2 into rho G by rho L, and UH is the velocity through the hole. And yesterday I have explained about the velocity through, in the comparison of the velocity through tap and shower. So UH is like a shower through the slots. It is coming as a shower. So the velocity will be more. Then K2 has got a equation 50.88 CV square, where then the CV can be obtained from the plot page 1443, figure 1435, that AH by AA is plotted against the discharge coefficient CV for various tray thickness, the ratio of thickness to diameter. Then you get it at 0.72. K2, the formula is 50.8 by 0.72 square, it is 98. Now what we have to get is UH. UH is a velocity. Use the law of conservation of mass. Since for liquid, this is volume is also okay. Gas at constant pressure and temperature only, law of conservation of volume is acceptable. Since the pressure of the column and temperature and pressure of the column are maintained constant, you can use law of conservation of volume also. So UH into AH is equal to UN into AN. You know UN and AN. UH alone can be found out. AH is also known. It is 23.24. HD you calculate. It is coming around 68.7. Then for beta, there is a formula Q by LW. What is Q? Q is the volumetric flow rate of the liquid. LW is the length of the wear. Here, the length of the wear. And HW is the height of the wear. Then another factor, FVH, is to be determined. That is the factor for flow through holes. The equation for FVH is equal to UH into rho G raised to 0.5. That you calculate 26.48. Then everything you put in the equation, you get it as beta as 0.289. Then for sieve plate, HW is the wear height, that you assume 40 mm. And HOW, height of the crust over the wear, there is an equation 664 into Q by LW raised to 2 by 3. Then here LW is equal to 70 mm here, 0.7 meter. Then you get it HOW. So HDS is equal to HW plus HOW. HW is 40. Add it, comes around 50.92. HL dash is equal to beta HDS. It is 14.72. If you add HD plus HL dash, it comes around 83.42 mm. Compared to the pressure is, you see, if you convert it into millimeter of water, you convert it into Pascal, it is coming around 817, very small. That is 0.817 kilopascal. Our atmosphere pressure is 1 into 10 raised to 5, so it is very, very negligible. Next is VP. That's also available in the 7th edition Peri only. For that, actually, there is a figure 1427. HW plus HOW is plotted against HD plus H sigma. The formula for H sigma is 409 into sigma by rho L into dH. Sigma is the surface tension. So all these values are known. So you calculate, and then there is a plots. You can see this is 69. What you get is HD plus sigma is 69. Much, whereas the plot is up to 60 only. So there is no issue. There is no VP. So that design criteria is okay. Next is HL. HL is the height of the liquid. For that, the formula is phi E into HW plus 15330 C into Q by phi e raised to 2 by 3. Then for that, then how would you find out C? To find out C, there is another formula. No, not these are all empirical formulas. When you use the empirical formulae, you have to see that the unit should be consistent with what are given in the text. So you can find out, see all the values are only HW is not known, HW is 40. So you find out C. Then phi, what is phi? Phi is e raised to minus 12.55 into Ks raised to 0.91. What you don't know is Ks, you don't know. Ks is equal to UA into rho G by rho L minus rho G raised to 0.5. These equations, all the equations are available in Peri. To find out UA is the velocity of the active area. Then again you make use of the same law of conservation of volume. An into Un is equal to UA into AA till it's coming around 1.4. Ks you find out it is 0.05. Then phi you have to find out phi is equal to 0.44. Phi is the fraction of the phi is HF by HL, phi E is equal to HL by HF. That is, HL is the height of the liquid and HF is the total height. That is, you are maintaining is 40 mm. That is lip of the wire. That is 40 mm. So they find out using the formula phi E you are getting 0.44. HL, the formula to find out HL is also given here. HL you are getting is 18.66. So phi E you know, so you will get the HF as the total height with 41.4. Whatever you assume is 40 mm, it's more or less correct. So liquid hold up is also okay. Then next is entrainment. What is entrainment? Entrainment is the amount of gases which is amount of liquid which is going along with the gas. This formula is psi is equal to E by Lm plus E. Everything is written here. Lm is the liquid flow rate in moles per second. Here you have to be careful. This is in gram mole. Whatever the liquid flow rate available is in kilogram mole. So you have to multiply into 1000 to get gram moles per second. Then substitute all these things and you will get L by G, and the formula is psi is equal to E by Lm plus E. And how to find out psi? Psi is to be obtained from graph, that is figure 1434 of page 1443. L by G into rho G by L raised to 0.054 for corresponding to 80% flooding. We are assuming flooding velocity is 80% of the actual velocity is 80% of the flooding velocity. The value of psi is equal to 0.07. Substitute, you will get the value as some 6 gram moles per second. That is also negligible. Next is you have to find out the downcomer flooding. That is also the HDA, downcomer head loss is equal to HDA 165.2 into Q by ADA, where ADA is the minimum flow area of the downcomer. Yesterday I have told about C into LW. LW is the length of the wire. C is the clearance. What is seal is equal to HDS minus seal. That is liquid seal. You assume that at the surface of the sieve plate, a small amount of water is maintained as a seal, and above only the flow is taking place. So HDS is already determined 50.92, and subtract 25, you get CS 25.92, ADA 18.14 into 10 raised to minus 3. Q is already known 5.22 into 10 raised to minus 5 meter cube per second. Substitute, you will get the all this can add HT already determined HW is 40, then HW plus HOW plus all these things you add, you will get value. Then HDC is equal to, you have to find out HDC dash, HDC by phi. Phi is the fraction of the liquid. It is 0. So you divide it, you will get somewhere 290. Then it is less than trace space. So all the design criteria are met. So all the designs okay. Now find the height. Height is equal to number of trace minus 1 into trace spacing. Yeah, so number of trace you got it as 7, isn't it? 8. So 8 minus 1 is equal to 7. 7 into 0.45 plus 1.5 meter each, the top and bottom, add together and assume an efficiency of 50%. So number of trays will be more. If the number of trays is 8, then for a 50% it will be 16. Then you subtract 1, then 15 into 0.45 plus 3. You get this is the design. So your design is safe and okay.